Inductor. Inductor is a passive two-terminal electrical component that stores energy in its magnetic field. So inductor is a passive electrical component. That means it is not capable of supplying energy. So it is a passive component. It is a two-terminal component. So an inductor is having two terminals and it is capable of storing energy in its magnetic field. So an inductor is obtained by twisting a conductor to form a coil. So if we twist a conductor in the shape of a coil, we will get an inductor. This is the circuit symbol of an inductor. So inductor is obtained by twisting a conductor to form a coil. Now, when a current flows through this inductor, a magnetic field will be produced around it. So we know that when a current flows through a conductor, when a current flows through any conductor, a magnetic field is produced around it. Similarly, when current flows through this inductive coil, a magnetic field is produced around the coil. And if the current flowing through the coil changes, this magnetic field also changes. And according to Faraday's law of electromagnetic induction, according to Faraday's law, whenever the magnetic flux linked with a coil changes or a conductor changes, an EMF is induced in it. So when the magnetic flux linked with this inductive coil changes, an EMF will be induced in this coil according to Faraday's law of electromagnetic induction. So when the current flows through this coil changes, the magnetic field around this coil changes, and as a result an EMF will be induced in it. Okay. And according to Lenz's law, the induced EMF will try to oppose the cause producing it. According to Lenz's law, the induced EMF always opposes the cause producing it. Here, the cause of production of induced EMF is the change in current I. So, induced EMF is produced due to the change in magnetic field, and the magnetic field changed due to the change in this current. So the ultimate cause of induced EMF is the change in current through the coil. So according to Lenz's law, the induced EMF will try to oppose the change in current, which is the cause of the induced EMF. So an inductor always opposes the change in current through it. This is the important feature of an inductor. An inductor always opposes the change in current through it. Inductor opposes the change in current flowing through it. So we have said that the induced EMF is produced due to the change in current, and thus the induced EMF will be proportional to the rate of change of current. Induced EMF is proportional to rate of change of current through the coil. That is, V is proportional to di by dt. Now, this proportionality can be replaced by a constant L. So, equation becomes V is equal to L into di by dt. This is the equation for voltage across an inductor. Voltage across an inductor is equal to L into di by dt, where L is the self-inductance of the coil. L is known as self-inductance or simply inductance of the coil, and its unit is Henry, denoted as capital letter H. Okay. So here L is self-inductance and di by dt is the rate of change of current through the coil. So voltage across an inductor is the product of its self-inductance and the rate of change of current. So now we can define the self-inductance as the property of the coil by which the coil opposes the change in current through it. So inductance is the property of this coil by which it opposes the change in current flowing through it. So now we have the equation for voltage V is equal to L into di by dt. Now from this equation we can write the equation for current. We can write di from this equation as V into dt divided by L. So we have V is equal to L into di by dt. From here we can write di is equal to V into dt divided by L, or 1 by L into V dt. Okay. So di is 1 by L into V dt. So from di we will get I by integrating this equation. So when integrating di we will get I. So current I is equal to integral of right hand side, that is 1 by L is a constant and integral of V dt. So this is the current equation for an inductor. Equation for current flowing through an inductor is 1 by self-inductance into integral of voltage across the inductor with respect to time. So I is equal to 1 by L into integral V dt. Now let us find out the power in this inductor. So we know the equation for power. Power is equal to voltage into current. Power is the product of voltage and current, which is equal to, so we have for an inductor V is equal to L into di by dt. So L into di by dt into current. Current is substituted as such. So L into di by dt into I, which is Li into di by dt. Now we can calculate energy by integrating power. So we know that energy is equal to power into time. So by multiplying power with the time we will get energy, or by integrating power with respect to time we will get energy. So energy is equal to integral of P dt, integrating power with respect to time. Now we have calculated as P as L into I into di by dt. So integral of L into I into di by dt into dt with respect to time. Now this dt and dt can be cancelled. Then integral of Li di. So what remains is integral of Li di. So here L is a constant. So L into integral of I di. So what will be the integral of I with respect to di? So we know integral T dt is equal to T square divided by 2, or integral x dx, simply integral x dx is equal to x square divided by 2. So integral I di will be I square divided by 2. So we will get the energy stored as L into I square divided by 2, or it can be rearranged as half into Li square. So energy stored in an inductor is equal to half into Li square. So this is an important equation. E is equal to half Li square. And the inductor stores this energy in its magnetic field. There will be a magnetic field around it, and the inductor stores this energy in the magnetic field. So equation for energy stored in an inductor, or equation for energy stored in a magnetic field, is energy is equal to half into Li square.